Hello and welcome to my Physics 2211 lab number 5. This is the Create Your Own Lab project, and I chose to do mine on the conservation of momentum. So as a brief introduction, the purpose of this experiment is to model the conservation of momentum of a low-speed impact and to compare the experimental results to an idealized model. And a summary of our results are that the real-world system does not appear to conserve momentum, primarily due to the effects of external forces. So the momentum of an object is defined by the equation P equals m times v, where m is the object's mass and v is the object's velocity. And in a closed system without the loss of energy to the surroundings, the sum of the momentum of both objects should be the same before and after the collision, as shown in the equation below. And to minimize the impact of the surroundings on the system, we take the initial and final speeds as close to the impact event as possible. So the procedures for the experiment are pretty straightforward. We started by recording the mass of 2 rolls of tape, and then launched the 2 rolls of tape at each other on a smooth floor, tracking their movement using Tracker while treating them as point masses. We then created 2 models using GlowScript, one which uses the experimental data, and one which models a perfectly elastic collision before comparing both. So you can see the system to the left. The blue tape and the white tape are considered part of the system, whereas the surroundings are the ground and the earth. The basketball is there as a size reference. The y-hat axis is upwards vertical, and the x-hat axis is rightward horizontal. So to establish momentum, we took the position at impact and position before impact, and then the delta t, or the change in time of a single frame, to get to the near instantaneous velocity prior to collision. And then with that velocity, we then multiplied it by the mass of the roll of tape to get its momentum. This process was repeated for each component vector, and also done after the collision, except obviously it would be the position after impact minus the position at impact. So to create the model, we started by defining both rolls of tape and their starting positions, and setting up the axis and origin. We then established the initial velocity and mass of both rolls of tape, and the change in time of a single frame. We then iterated the position up to the moment of impact using that velocity, and then updated the observed post-impact velocity manually before iterating the movement post-impact using position and update formula. Finally, we did momentum calculations, taking the observed velocity immediately before and after impact and comparing momentums before making them visible via a print statement. For the second model, to create the idealized elastic collision, we simply took the observed velocity immediately before collision and multiplied it by -1 to invert it, such that both objects are repelled with a velocity of equal magnitude to the previous condition. Note the 2 rolls vectors don't have to have the same angle or magnitude before and after to be conserved, so long as the amount of kinetic energy is constant. The simulation above is the most simple way to show the concept, but not the only one. You see here our observed model, which slows down dramatically afterwards in the ideal elastic collision in which both objects bounce perfectly off one another. So was momentum not conserved? So as a control, the idealized elastic collision shows the conservation of momentum while confirming the validity model, as momentum before and after was equal to 0.095. Whereas the experimental model suggests that momentum was not conserved following the collision. However, there are several limitations in the model which explain these results. Of course, obviously, the momentum went from 0.095 to 0.029. So why does momentum not appear to be conserved? So the 2 rolls of tape are not a closed system. The floor acts as part of the surroundings and imparts a force of friction, decreasing the velocity over time. At the moment of collision, some of the translational kinetic energy is also transformed into rotational kinetic energy as the impact induces spin, and this cannot be accounted for by measuring the distance over time, as we are treating both objects as point masses, which can only have translational kinetic energy. So how could the experiment be expanded or improved? Making the system more resistant to the effects of the surroundings by using more massive objects on a floor with less friction would improve the accuracy of the model, and taking the pre and post velocity closer to the moment of collision would show momentum being more conserved, but this is limited to the frame rate of the camera. Thank you.